Hi, my name is Seth Temple. I am a PhD student at University of Washington, studying statistics with applications to public health and genetics. Today, I will be giving a talk about two data analyses of Culex mosquitoes and West Nile virus. This is collaborative work with Los Alamos National Laboratory, especially Kimberly Kalfeld and Morgan Gores. So today I'm going to talk about Culex mosquitoes and West Nile virus. West Nile virus is an infectious pathogen that impacts the nervous system. So for most people who get West Nile virus, it might cause a fever or a rash. And in severe cases, it can lead to hemorrhagic fever. So this is if your brain is bleeding, or a meningitis. So your nervous system will stiffen up and you'll have a very stiff neck. These complications can be fatal, and this is the motivation of this work. So the first cases of West Nile virus arrived in North America in 1999. And in the early 2000s, there would be news headlines about, these apocalyptic scenes of crows dying in the streets, of horses dying. And so this concerned a lot of people and has led to an epidemiological response. So how does this operate? So essentially, mosquitoes will bite birds who harbor West Nile virus. And then with the West Nile virus in their saliva, they'll go on to bite humans or livestock. And so this transmission cycle is being depicted here on the right. So we have a cycle that's called an enzootic cycle, in which the virus is maintained naturally in the environment. So there's about 400 bird species that can harbor the virus. And then the mosquitoes will keep biting the birds and spreading it about the bird populations. In some instances, they will bite the accidental hosts, which are humans and horses, and this can cause severe symptoms. So because it's maintained in this enzootic cycle, climate and environmental change is important in how it might affect the bird populations or the mosquito populations. So in my first project, I'll talk about updating the geographic ranges for Culex species. So we want to describe the range for 7 species within the Culex genus across North and South America. The research question is, which habitats do the Culex mosquitoes favor? And our approach was to collect a bunch of data. So first we got a bunch of observations of mosquitoes across these continents. And then we collected weather, climate, and land type information from satellite imagery. We built a model that would associate the mosquito presences with these environmental conditions. And so we're able to train this model on a large collection of data points, and then we try to extrapolate our model inferences to new areas in the continent. So here we're looking at the observations that we have from 5 or 6 data repositories. So in purple, we have icons that signal presences from the Washington Department of Health. In red, we have some presences that signal data from the Public Health Ontario Department. And you'll see that we have some observations in some Midwestern states, some states in the American West. You will also note this gray outline, which is a historical range map for the Culex tarsalis species. And this is from about 1980. So in our work, we'd like to update this range map and see how it may have changed in the intervening 40 years. So this map is showing our model estimates for habitat suitability. Here, the scale is identifying that the darker blues are more suitable habitats for Culex tarsalis. And our range map is similar to the 1980 map. And we are identifying that the Midwest and the American West seem to have suitable environments for this species. the role that I play as a statistical consultant is identifying the limitations of our methods. And so one serious limitation is that we collected data mainly from temperate and tropical regions, and then we tried to apply our model to a continental scale. And so in this map, we have identified in pink areas in which there's novel conditions, so environmental conditions that are very different from the training data. And so we don't want to assign too much confidence in this estimation for these polar regions of Canada. In conclusion, we have identified some northward expansions of Culex species. And we believe this is really being driven by increasing global temperatures, as the temperatures are important to both the spawning behavior and the survival through winter of the mosquito species, but also the proliferation and replication of the virus. And I should say this is the first continental distribution map for these species. So previous efforts have emphasized wealthy countries like the US and Canada, but we're now providing some inference for many countries in Central America and South America. We also want to make sure that we're correctly explaining some of the uncertainty, where in areas in South America and in polar regions, we have less data and accordingly less certainty in our estimation. Project 2 is a new statistical method to directly study West Nile virus. And this is my first author paper, which is currently under review. The summary of this project is that we're extending a method used in wildlife ecology to vector-borne pathogens. So previous efforts to study West Nile virus have looked at the abundance of Culex species as a proxy for West Nile virus threats. Here we have viral test data from mosquito pools in Ontario, Canada, and so we can directly study the virus and not just like a proxy, which is mosquito abundance. And we want to make sure that we communicate uncertainty and limitations in our estimation procedure in a statistically principled way. The research questions are to look at the environmental and surveillance conditions and how those impact the viral data, both in space and in time. And so our approach is to construct various linear models and to provide some uncertainty about the model effects in these linear equations. The motivation for this work is that West Nile virus incidence goes through peaks and troughs. So in 2002, 2012, and 2017, there was an abundance of West Nile virus positive cases, versus in years like 2009, there was much less West Nile virus. So we want to see if environmental covariates can explain these changes in West Nile virus year over year. Our model has to distinguish what is referred to as occupancy and detection. So imagine a researcher is going into a forest to look for a species. If they find the species, we say that species is detected, and therefore it must occupy the forest. If the researcher doesn't find the species when they go on a short walk in the forest, well, it's not detected. In this setting, we need to clarify, was it not detected because the species doesn't occupy or live in the forest? Or was it not detected because we didn't do a more thorough study of the forest to find the species? So we can construct such models where we have these like nested component models. And we do this in a linear way where we relate the log odds of an occupancy or detection probability to a linear equation. So you can imagine you have data covariates, for example, environmental conditions, and you'll apply weights or model effects to each of those data values. So we did this for an occupancy model, and we did this for a detection model. And the detection covariates will focus more on the number of traps that were studied, the density of mosquitoes, and the proportion of Culex in those traps. So between the covariates, for some of the model effects, we see strong evidence that the effect is not zero. So that's the case of temperature. We believe temperature is principally important to the spread of West Nile virus. On the other hand, West Nile, the bird diversity is more weakly associated with West Nile virus prevalence. It has an association, but it also overlaps zero in its quantile range. We can visualize uncertainty in time for our model outputs of occupancy detection. So here I'm looking at 4 of 34 public health units in Ontario. In blue, we have Toronto. In purple, we have a region near Detroit. In red, we have Ottawa, the capital of Canada. And in green, we have a county in Northern Ontario. And the mosquito season ranges from epidemic week 20 to 40, which is about May to October. And we see a peak in occupancy in about July and August in the warm summers. And accordingly, we see that these public health departments increase their efforts to detect the virus in these periods. Finally, we can visualize our model in space and time. So I'm showing this GIF. It's updating from epidemic weeks 20 to 40, and the warmer temperatures are a higher occupancy probability. In conclusion, we introduced a new method for vector-borne epidemiology. So we can use this method to study other mosquito-borne diseases, for example, Zika or dengue. We can apply this to other species spread by insect vectors. An example would be Lyme disease and ticks. And we can study other spatial regions, for example, the 37 counties in Washington state. And this method has been specially designed to try and characterize uncertainty in estimation. This is very important because we understand that there's climate and environmental change going on all of the time. And also, we're trying to study a large spatial region, on the order of large countries or entire continents. And so there's limitations in the data that we have, and we want to be able to characterize the uncertainty in our inference. So I'll just conclude by saying, if you want to become a citizen scientist, you can contribute to the repositories of iNaturalist and eBird while you're out hiking or going on walks. If you want to learn more about West Nile virus, there's an excellent podcast, episode 84 of This Podcast Will Kill You. And I'll just conclude by saying thank you for listening, and I'm open to questions.